Good morning, Walter. I'm really pleased to be talking to you today. And we're going to talk about POI today, Precision Oncology Ireland. Could you tell me what is Precision Oncology Ireland, please?
Yeah, first of all, thanks for coming and meeting us. It's very pleased that you're here. Precision Oncology Ireland is basically what the name says. We're trying to be more precise in terms of diagnosing and treating cancer patients. And that is now possible because we have really new technologies. So in the last 10, 15 years, we have a treasure trove of new technologies like genome sequencing, but also other means where we now can actually very precisely look what's wrong with the person. So we can do this better, more precise than we ever could this before. And that means we now can actually try to treat individual patients according to exactly their needs and exactly their disease. And what POI tries to do is bring these advances which were made in basic research. These were all discoveries and things which come straight out of the laboratory, make this useful for the cancer patients in the shortest possible way. So it is a research project. We do research and that's the main focus. But the outcome will be something what we think and hope will be very useful for making cancer treatments more precise and so that the patients have a better treatment, but also better quality of life because we can lessen side effects while keeping the efficacy of the treatment.
I understand. So when you say that I'm wondering who is involved in this with you?
Oh yeah, that's a good point. This is actually a fairly unique consortium. It is 5 Irish universities. So it's literally almost all the academics in Ireland working on cancer. But very importantly, it's also 6 cancer charities, and we are very happy and pleased that we have them on board, including Breakthrough, and then 8 industry partners. So this mix between academia, charities, and industry is actually fairly new. And I think it's not only a unique trait, but we also need this because we need to depart from sort of seeing cancer and disease as, here's the patient and we try to treat the patient. We need to see this as a collaborative joint endeavor, where we all work together in trying to address this devastating disease on many different levels. Of course, the patient is in the center, but we need industry because they develop the drugs. We need the charities because they are the ones who are on the front line with the patients. They know what the patients want. They care for the patients. We need the academics and the scientists because they do the research. The clinicians in the hospital treat the patients. So we need to see this as a sort of much more holistic endeavor, where we tackle cancer, not individually, but as a group.
So on a day-to-day level or a month-to-month level, how are you doing this?
It is, so there is different levels. The mainstay is research. So this is done in buildings like this, in laboratories, but also increasingly on computers. A lot of the research nowadays, especially with these new methods, is actually analyzing the data. We are very quick and fast now in producing data. So for instance, the first sequence of a human genome took 10 years and $3 billion. Now we can sequence a human genome basically in one afternoon for about $1,000. So it is now feasible to do this for every cancer patient, but we actually need, 3-4 hours to sequence it, but then we need 3-4 days to analyze it. So we are much more busy now with actually analyzing all this data and making the models where we can then determine what is the best possible therapy or what is the most accurate diagnosis for a patient. So there's a close integration between data generating, data analysis, and of course the data come from our clinical colleagues. So there's also a very close interaction with the clinicians. And the POI is distributed around the whole country. So there's a lot of different things happening in Galway, in Cork, in Dublin at the same time. And so we have, fortunately also to these communication technologies, we can now have meetings on Zoom or telephone very easily. So we can sort of coordinate what's happening, and this is also one of the great things because we really can leverage all the good things which are around the country very quickly and very easily. So we work in the labs, we work in the clinic, and we work together mainly virtually, but we are now used to very well to working virtually anyway. So, it is really a great mixture of doing research with data, doing research in the lab, doing research in the clinic, working with patients, working with industry, working with the charities. It's a completely new model, but it's also very exciting because for the first time it really addresses everything we can address.
Exactly. You have talked about the patient, and you've mentioned the patient and how important this is for the patient. So could you talk a little bit more about that?
Yeah, I think there is now a general, I would say almost a revolution in medicine. So first of all, I personally think medicine is becoming more a data-driven science. But medicine is also now returning back to becoming more personal. Medicine used to be very, very personal. It's still very personal, but we have specialized so much that we sometimes lose a little bit sight of the context. But now with these modern technologies and also with the way the thinking has changed, is that we concentrate now more on the person again. And that means we are trying to consider diseases in context, not like this is a cancer and we just look at the cancer. We look at the whole patient. We look at what they eat, how they feel, what other diseases they have, and how we can address this as a whole person.
So you're kind of targeting or tailoring a treatment program for each patient.
So that's what we are trying. At the moment, this is all research, but this is what we hope in 3 to 5 years will actually come into the clinic. And the other thing is that patients used to be sort of seen as clients, and that has fundamentally changed, fortunately. So we now patients' role is more as a collaborator, because of course we need patients for our research. We need the patient samples, but we also need to listen to their opinions and hear what they have to say, because we haven't experienced that, and it always looks very different if you're actually experiencing something than if you're from the outside. So this is I think really important that we have this model where patients, researchers and clinicians are collaborating and working together.
Mm-hmm. Tell me, what is your ultimate achievement then? What do you hope for ultimately with this? Is it from the research area, or is it the clinician area? What is your hope?
So the ultimate goal is making research work for the cancer patient. So as I said, it's a research project, but the outcome will be that we have results which will lead to clinical trials, which will lead to new concepts in cancer therapy. For instance, immunotherapies is now something what is, everybody knows about this. And they're very effective, but unfortunately they are only effective for a very small group of people. And one of the things we're trying to do is actually making them effective for a bigger group of people. And that's done through research, but the hope is of course that if the research is successful, we then will have immunotherapies which don't help 20 or 30% of people, of patients, but maybe 50, 60, 70%.
Exactly. So it'll transcribe. The research success will transcribe. Walter, I'm just wondering, I had breast cancer, and I'm just wondering, how would my treatment differ now using the Precision Oncology? I had invasive lobular breast cancer. I had 2 tumours. One was HER2 positive and one was estrogen positive. I had a lumpectomy. Then I had 17 sessions of a Herceptin, 5 with chemotherapy. Then I had radiotherapy, 35 sessions. And then I'm still taking an estrogen blocker 5 years later. So using what you know now, Might my treatment differ now?
It may be. I mean, the treatment you received seems to be very comprehensive, and also it's a complicated situation having two tumors which are biologically very different. So this is unusual. But the treatment nowadays would probably start with that. First of all, the tumor would be sequenced. So we would determine a genome sequence of the tumor.
Could you just explain that in non-scientific language, if it's possible,
Yeah,
for me?
So what basically is our blueprint for how we all created are the genes.
That's right.
And we have about only 20,000 of them. Doesn't sound much, but that translates into about 3 billion base pairs. These are the letters, which basically, it's like an alphabet with 4 letters, and that makes the genes. So it's like a book in a language written, which is only 4 letters. But if you would staple this here on the table, it would reach up 150, about 3 meters high. And this is what sequencing means. We basically read it. We read the text of our genes. And because the text is only 4 letters and it's very long, we need computers to actually decipher it, to sort of make sense out of it. But what we can do is then determine whether there is any changes in the genome. So for instance, mutations where letters are changed, which then change the sense of a word or the function of a gene. Or sometimes you have deletions, that means there's pieces missing. Or sometimes you have amplification, that means certain pieces are just like multiplied. And that all can change the function of your cell. And this is actually the cause of the vast majority of tumors, that you have these genetic changes, which then cause the cells to not respect what they should normally be doing, but become haywire and just grow like mad and form tumors. So this is one very important aspect. And by sequencing, what we call sequencing, basically reading this information, we nowadays can match these genetic changes to certain drugs. So we have certain drugs which are specific, addressing some of these genetic changes. We need many more of those drugs, but the concept in principle works. So we can match genetic changes to some of the drugs which we have, and there is a whole lot of efforts now going on to make more of such drugs, because this is actually one way how we can be very precise. Because even unless you are identical twin, your genomes are not the same. They are all different. And by being able to read the differences, we then can really exactly choose what would be the best drug for a particular person. And so this is already in the clinic now. This is very powerful. But there is still a whole lot of that language which we don't understand. We know of this 3 billion long code. We probably know maybe half at best. And we have no idea what the other half means. It's simply a book which we haven't read, chapters which we haven't read. But in order to understand them, we need to invest more research, because the problem is not that we have 20,000 genes. The problem is we only have 20,000 genes. So for instance, these trees have more genes than we have.
Really?
Yes. Or wheat has 60 times more genes than we have. And this is exactly the issue. Our genes work by being very cooperative. So if one gene only would do one thing all the time, we would have cracked the code already. We would know what every gene is doing. But it's like in a party. One gene can talk to another gene for a while, then they talk to a third, then they form a group of 5, then they go away, talk to somebody else. So it's this combinatorial complexity which makes it so difficult. And this is also why we need more methods just than genetics. We need all these other, what we call omics technologies, where we also look at proteins, where we look at metabolites. These are the breakdowns of the food we eat. because this gives us this more dynamic information, the sort of real-time information, what's happening here and now, and which gene talks to which other gene.
Yes.
And this is how we can, again, become much more precise, but again, that opens, for instance, then new avenues, like, for instance, what role does our environment play? What role does our food play? And we already know that all these things can contribute to cancer and can contribute to cancer therapy. But we don't know exactly, for instance, what may be healthy for you to eat may not be healthy for me to eat.
Exactly. So again, going back to what you might do for me that might differ because of the precision oncology, that's the first thing you would do is the
sequencing the genome, yeah.
Okay.
The second thing in, let's say, if POI is a huge success and we bring this in the clinic in 5 years' time, the next thing we would do is a computer model of your tumor. And we would simulate on the computer how the tumor grows, how it will advance, if we wouldn't treat it at all, how it would advance, in 2 years' time, 5 years' time. We also can simulate different therapies. So we would try out on the computer first, does this work? Does this work? Does this work? And then we would choose the one which we think works the best. And since you had 2 very different tumors, we would do it for both. And then we, for instance, would also look what doesn't work, and exclude unnecessary treatment. And this is actually very important. I mean, you've been through this, quality of life is very much...
It was going to be my next question.
Okay, so I'll stop here.
How the patient's quality of life during treatment would improve because of precision oncology? Or you would hope to improve?
We hope so, and I'm very confident it will improve, because at the moment, unfortunately, when you say patient doesn't respond to therapy, that means usually they don't derive a benefit, but they still have the side effects.
Yes.
And by choosing treatments which really will help the patients, you still have the side effects, but you avoid side effects in patients where the treatment doesn't help.
Exactly.
And in a second step, you actually can go about minimizing side effects. So for instance, by combining drugs. So you take drug A and drug B, they each have side effects. But if by combining them, we need less dose of each, then we minimize the side effects, but still reach a good effect.
And hospital stays surely might be shorter for patients as well?
Yeah, I mean, the side effects are one of the major things why people have to stay in hospital for a long time, and also why they can't return to work. And I mean, you know this much better than me, but it is important, to start leading a normal life again. And the sooner you can enable this, I think the better the patients will recover.
That's right, yes, very much so. Again, I'd just love you to clarify very briefly, I suppose, the huge impact this will have in the future on the treatment of cancers.
Yeah, so we really believe that this will be changing, the way how we think about cancer, the way how we research cancer, the way how we diagnose cancer and how we treat cancer. And the first line will really be that we have better diagnostics, because with this genome sequencing and so forth, we can be very precise. The second step will be, because of these computational models, we can try out treatments on the computer and then give the patient the best treatment we can come up with. And we can do this on a very individual basis. But then thinking even farther ahead, like 10 years ahead, we probably will be able to do much more in terms of prevention. Because at the moment, well, we all know smoking is bad and other things are bad. But we don't know this for a particular person. And with these computer models and these molecular features which we can draw information from, we should be able to actually say, you can eat ice cream, that's fine, but you should avoid avocados. I'm just making this up now, but we can be very individual, become very individual in terms of what is good and bad, and we probably can gauge much better what adjustments, for instance, in lifestyle you can do to live better.
Excellent. And at the same time, in your research, are you actually developing drugs at
Yes,
Precision?
it is a small part, but for instance, I myself have one project with the Children's Research Hospital where we actually try to look at completely new targets for neuroblastoma. This is normally treated with chemotherapy, which is basically we try to kill the cancer cell by damaging them so badly that they can't recover. But of course, there's collateral damage that also damages normal cells. And if you give this to a baby, you can imagine that this has sometimes really long-term, very bad side effects. And so we are trying to find new ways where we don't need to damage the genome, but we still get a good therapy effect.
Excellent. Thank you very much for explaining
You're very welcome.
Precision Oncology Ireland. I do understand a little bit more now, and I'm delighted to talk to you this morning.
Yeah, I'm delighted that we had this opportunity. Thank you very much.